Good afternoon, everyone. My name is Asmita Bhadri, and today I'm going to be presenting the topic Edge Computing in Smart Grid Applications as part of my AET in Advances in Energy Technology. So, what exactly is edge computing? Edge computing is a distributed computing framework that brings data processing and storage closer to the devices and users that generate the data rather than relying solely on centralized clouds or data centers. This approach reduces latency, conserves bandwidth, and enables real time responsiveness for applications that require immediate insights, such as autonomous vehicles and industrial IoT. Now, how does this work? Instead of sending raw data to a distant data center for analysis, edge computing performs computations at the edge, that is, at the periphery of the network, near the source of the data. This local processing takes place on various devices, such as IoT devices, local edge servers, as well as embedded systems. So, like we've studied before, electricity has been the backbone of every modern technology, from lighting and transport to today's digital economy. But with demand for electricity expected to rise by 70% until 2050, how do we make sure that our power grids are reliable, secure, and efficient? Well, this is where smart grids powered by IoT and edge computing comes into the picture. So, to further understand the concept of smart grids, let's first differentiate how it's better than traditional grids. So as we get to traditional grids, it offers a unidirectional flow. That is, the flow moves from the power plants to the transmission lines and finally to the end user, which is the consumers. The challenges posed by such a technology is that it wastes energy, lacks real-time monitoring, poses multiple security issues, and also has rising electricity costs. Smart grids, on the other hand, offer a two-way communication of electricity and data supported by IoT sensors and smart meters. Now, where does edge computing fit into this landscape? So, cloud computing was once enough, but billions of IoT devices now create too much data, delays, and costs. Edge computing processes data closer to where it's generated, that is, at the edge, at the periphery, cutting latency and enabling real-time decision making. Benefits? It offers faster responses, reduces the bandwidth, real-time monitoring, and efficient energy use. Now, to understand the entire IoT architecture better, let's look at this diagram, which gives us a gist and a brief understanding of the layers involved within this architecture. So this comprises of primarily four layers. The first being the things layer. So things layer indicate the different devices that are deployed within the network, mostly comprising the inverters, sensors, and actuators. Moving on to the network layer, the one layer that bridges the gap between the database and the devices deployed on the network. This offers communication technologies such as WiMAX, LTE, Sigfox, LoRa, NB-IoT, Wi-Fi, Bluetooth, NFC, and etc. Middleware layer, which is the third layer. This layer comprises the database, the storage system of the entire IoT device, and also the layer that comprises all the computational needs. It also helps make decisions. Lastly, the application layer, the one layer that helps us contact and control these devices. Smart applications such as power distribution monitoring, advanced metering, and microgrid systems are facilitated by this layer. Now, what are the applications of edge and IoT smart grids? The three most prominent ones are listed here as power distribution systems, microgrids, which are mostly used in homes, factories, and communities, and advanced metering systems. Coming to power distribution systems, these are real-time monitoring of renewable energy sources like solar or wind. Example, AI-based control of inverters at the edge to stabilize voltage. Microgrids are deployed at homes, factories, and communities. These optimize load management and help build smart factories using edge-based algorithms to balance cost and power. It also offers peer-to-peer solar energy trading via new technologies like blockchain. Advanced metering systems. This system comprises of smart meters providing real-time consumption data, for example, identifying abnormal usage, integrating solar panels at homes. So another prominent application of IoT in smart grids is SCADA, more popularly known as supervisory control and data acquisition. SCADA is a control system architecture that collects real-time data from sensors, meters, and devices across the grid and allows operators to supervise and control the entire power system. Traditionally, SCADA systems were centralized, but with IoT and edge computing, they are becoming more distributed, intelligent, and faster. So as you can see, this comprises the cloud layer, the edge layer, and the thin layer, like we discussed earlier. And the cloud layer comprises of the cloud or the internet, of the cloud SCADA database, the data processing center, as well as the final HTTP ends, which is HTTPS, DDS, and the REST services. And these help the electrical personnel make decisions. Now, this is bounded to the edge layer using the API service. The edge layer comprises of the local router, the gateway internet, and the local SCADA servers, which are in touch with the emergency control and monitoring service. Lastly, but not least, the things layer. This controls the power generation and the power distribution systems. So how do we fit SCADA into the smart grid architecture? The things layer, which is the field devices, contains IoT devices like smart meters, current or voltage sensors, temperature sensors, and actuators. These devices continuously capture live data such as power load, grid faults, or renewable generation. Communication can happen through Wi-Fi, Zigbee, NB-IoT, or even 5G. The edge layer, which helps process at the edge. Traditionally, all collected data would be sent to a central server or cloud. With edge computing, local SCADA servers, gateways, and routers now process much of this data closer to the source. This reduces latency, enables faster fault detection, and allows real-time actions such as disconnecting a faulty line or adjusting energy flow. Cloud layer. This layer offers centralized monitoring as well as analytics. Once pre-processed at the edge, data is forwarded to cloud SCADA servers. Here it is aggregated for long-term storage, advanced analytics, predictive maintenance, and is the largest option for decision making. Operators can visualize dashboards, track trends, and set up alarms or automated responses. Now that we've understood exactly what the architecture is and the benefits that it has to offer, let's take a look at the challenges and the future outlook. So one of them being scalability and reliability. As billions of IoT devices connect to the grid, data traffic grows exponentially, causing delays and bandwidth stress. Reliable edge infrastructures must be built to handle dynamic loads and ensure uninterrupted energy supply. Let's look at the second point, sustainability. Smart grids must efficiently integrate renewable sources like solar and wind without compromising stability. Edge computing enables smarter load balancing and energy optimization to lower carbon footprints. The third point, security and privacy. Distributed IoT devices increase exposure to cyber attacks from data theft to false data injection. Blockchain, lightweight encryption, and secure communication protocols are needed to safeguard energy data. Lastly, flexibility. Energy demand is unpredictable and depends on user behavior, weather, and industry cycles. Thank you.